Hello everyone, thank you for the introduction. I'm going to present a joint work with Juqiu, Mingji, and Jiayi, entitled From an Old Arity Signature to a Holant Dichotomy. To begin with, let me show you an example of Holant. Well, let's see the problem of counting perfect matchings in a certain graph. In this graph, you can see that there are actually two perfect matchings, and this is very trivial. And in the view of Holant, we view each edge as a Boolean variable appearing exactly twice. And each vertex is assigned a signature, or you can see it as a local constraint function, or if you have some knowledge from tensor network, a tensor, that is a mapping that maps its incident edges to a complex number. Also, the whole graph now is considered as a signature grid, which is considered as the input of this problem. Also, this can be seen as a tensor network. And for each variable assignment, such like this, the weight of it is computed like this, because under this variable assignment, each signature assigned to each vertex has its input and it will output a value. The product of all the output value is the weight of this variable assignment. And our goal is to contribute the partition function, which is, well, we enumerate all the possible assignment and we calculate their sum of their weights. So we can see that under this problem, well, if we assign 1 to this edge and this edge and 0 to other edges, for each vertex, there are exactly 1 edges incident to it is assigned 1, and all other edges are assigned to 0. So actually, if we this constraint is actually called exact 1 constraint. And also, if there are 2 incident edges assigned 1, then the property is violated and it's not counted as a perfect matching. So actually, in this instance, the partition function is just a number of perfect matchings in this graph. So let's go for some formal definitions. A signature of F is just a mapping that maps several variables to a certain number. And in this talk, we are focused on complex valued Boolean signatures, which maps several Boolean variables to a complex number. And a signature grid consists of a graph G and a mapping pi. This mapping pi just assign each a signature from a certain signature set F to each vertex. And it also gives each vertex a linear order of the edges, telling that, well, which edge is the first variable and which edge is the second. And the Holant is defined as follows. So the input is just a signature grid, and the output is what I said it is a partition function, and it has such a formula. Also, naturally, we can also define a bipartite version of Holant, right like this. In this kind of problems, well, the signature grid now is a bipartite graph, and we have to assign a signature from F to all the vertices in the left side, and a signature from G to each vertex from the right side. And the output is still the same, the partition function. So any problems with the definition? Okay. So now I'm going to introduce a very important concept called symmetric signatures, which are some very easy, comparatively easy signatures. Well, these signatures only, well, for a signature as it maps to, for example, it maps R variables to a certain number, it has actually 2 to the R entries. But these symmetric signatures, its output just depends on the Hamming weight or the number of ones of the input. So actually, it only has R+1 entries, and this makes it can be expressed as a vector like this, and where Fi is output on inputs of Hamming weight I. And there are some very important examples of symmetric signatures. For example, delta 0. It has the ability to fix a variable to 0 in a signature grid, and delta 1, it has the ability to fix the variable to 1. Also, there are equality k signatures that requires the k variables to take the same value, otherwise it will output a 0. And also, this equality 2, it asks the two variables to take the opposite values. And finally, exactly 1, it just requires exactly one variable in the input to take the value 1 and all other variables to take the value 0. And here are some examples of Holant problems. And you can see from this slide that Holant problem is very expressive. First, as I just said, counting perfect matchings can be generalized to a Holant problems that are defined by exact 1 signatures. Also, counting constraint satisfaction problems, which is another counting framework. Each variable can appear arbitrary times compared to Holant, but it can still be expressed as a Holant problems. We just need to replace each variables with equality k signatures to make the k variables that appear exactly twice equal. So actually, we can in this way we can turn a number set P problem to a Holant problem. Finally, counting Eulerian orientations for regular graphs can be expressed as this form. Here, this equality 2 on the left side can represent an orientation of an edge as you can always assign 1 to its head and 0 to its tail, and this represents an orientation. And the signatures on the right side is just the restriction of Eulerian orientation that it should have the same number of ingoing and outgoing edges. Okay. Now, another important reason for us to study the Holant problem is that Holant problem allows a certain transformation called holographic transformation. To explain this transformation, we can see this graph. At first is a bipartite Holant problem, and if we add some binary modifications, t and its inverse on each edge, actually they has no effect because they are just equal to equality 2. Yeah, but then we contract the t to the signature on the right side and the inverse of t to the left side. Then we get a problem that looks maybe very different from the original problems, and these two problems are still equivalent. And for another example, let K be such a matrix, and it can be computed that equality 2 transformed by this matrix will become this equality 2. And then, as we can always use equality 2 signatures to represent a variable that appears exactly 2 times, we have this reduction, and finally we turn the equality to the disequality, and this is very interesting because you cannot imagine this in the decision world. Yeah. And for simplicity, we just use K Holant to write this. So you know that when I mean K, the edges are orientations. Yeah. And there is a long line studying the Holant problems. And usually to completely classify the Holant problem, the complexity of Holant problem is very hard. And you can see there is a very large amount of work focusing on this problem. The work usually starts with the classification for symmetric signatures, and there are several results. And then it comes to signatures that are not necessarily to be symmetric. And also with some, maybe today I'm talking about complex values, but usually study begins with real values or non-negative values. And we also sometimes it is still too hard, and we need some signatures to help us to prove the hardness. So for Holant star, it has all kinds of unary signatures, which means signatures of degree 1. And for Holant C, it has two specific unary signatures. And for Holant odd, it requires F to contain a signature of odd arity. Yeah, and And this is and our results lies here, I think. Yeah, and you can see that there has been a year gap between our results and the previous results. Yeah. And now I'm going to present our main contribution. And our results actually we have actually two results that are very important. The first result is about the decomposition lemma. This lemma is also often used in the hardness proof in the previous study, and we prove that, well, for this problem, if we have F tensor G in hand, either we can know its complexity, or we can just use F and G separately. And based on this lemma, we prove a dichotomy for Holant odd, which means that F contains the signature of odd arity. Then Holant F is either in FP2NP or Sharpie hard. And I should remark that the FP2 complexity class FP2NP is introduced in this dichotomy, which is a dichotomy for so-called number U problems. And luckily, it's well believed that an algorithm with NP oracle cannot save all the number Sharpie hard problems. So actually, this do separate the complexity. And our results only introduce this NP oracle, this algorithm with NP oracle from this article. So if you can improve the algorithm in this article, then we can say maybe it's polynomial time computable or Sharpie hard, just like other dichotomies. And to start with, let me introduce the decomposition lemma. Well, the background is that, well, this statement is always used in the previous study, that if you get F tensor G, you always want to use F and G separately. And if F equals to G, or both F or G are not vanishing, vanishing means that, well, if the signature, if each signature grid over it equals to 0, then actually it is vanishing. So if it satisfies these conditions, then this statements hold. And this lemma has been widely adapted in later works to prove dichotomies. And however, for the complex valued case, this is not always true due to the existence of the vanishing signatures. And our dichotomy proves that, well, you can always use this statement, or otherwise the complexity of it can already be classified using a dichotomy in the previous study. And now I'm going to introduce the dichotomy for Holant odd. Okay, I think I'm going too fast. For a dichotomy, we always want to say, well, in some cases there are algorithms, and in some cases it is Sharpie hard. And actually, there are 7 tractable cases, 5 cases polynomial time computable, and 2 cases we only know that it is in FP2NP. And all these algorithms have been studied in the previous study, so we just need to focus on the hardness proof. And in the hardness proof, there are many cases. For example, for Holant odd, it begins with 3 cases, and we just reduce certain problems from the head to reduce it to the original problems. And you can see that there are lots of case analysis, but finally we reduce either Holant with delta 0 signature or problems with known dichotomies. Well, in fact, there are hard problems to Holant odd to prove the hardness. And actually, this framework is also used in the proof for real valued Holant dichotomy. And our main difference is that, well, most unary signatures in the real value setting can be directly transformed into delta 0. But in our settings, there are 2 exceptions, which if you view it in a K-Holant view, it's delta 0 and delta 1. Such signatures have the properties that if you contact 2 unary signatures together, it has a value 0, because you can see that we are linking them with this equality 2. So fixed to 0 is equal to fixed to 0. So 0 does not equal to 0. So this kind of unary signature just disappears if you contribute to a zero factor if you connect them together. So we have to analyze them separately, and we also establish several reductions to deal with this case. And then we go on with the problem of Holant with, maybe I should touch this. Then we go on with the Holant problem with delta zero signature. Remember that in the previous dichotomy, there is a dichotomy for Holant C problems where both delta zero and delta one are available. And in our work, well, there is only one signature, so proofs seems a little bit okay. Looks a little different because there is a certain case that we can only realize one kind of unary signatures, and in this case, luckily, if we want to prove the hardness, we can use other ways to, well, this is something like a closure, and this closure itself is easy. So we can assume that there is a signature out of this closure, and we can use these signatures to either produce delta one again or to finish our original proof. Okay. Now, too fast. Now I'm going to conclude these results. And to conclude, our ultimate goal is still to establish a dichotomy for complex-valued Boolean Holant. And our work has already given an FP to NP dichotomy for Holant odd, which means that there exists a signature of odd arity belongs to the signature set. So the only left case is that the signature set only consists of signatures of even arity, and this case is in fact really hard because when you connect signatures of even arity to another signatures, then it is still of even arity, and you must analyze them on something, use something very using some very non-trivial method. And our dichotomy also generalizes some previous dichotomies, and there are other related works that have not been encompassed by other works. So there are the dichotomy for symmetric Holant problems, for real-valued Holant, for so-called 8-vertex module, and what we use the FP to NP dichotomy for number U problems. And so the open problems is quite simple. So ultimate goal, can we solve this? Or can we find a p-time algorithm to replace this somehow ugly FP to NP algorithm? And finally, we can always study these problems over planar graphs, which is another very long line of studies. And that's all, I think. Thank you.